Many of you already heard the introduction of Ben during the summer school. Trying to see if okay. So apparently I need to introduce Ben Smith. Ben is a researcher at INRIA and the École Polytechnique, École Polytechnique, right? Yeah. Yeah, it says on the slides. He's been involved in a lot of public key algorithms and a lot of mathematics in cryptography. And it's a great pleasure to have him here with us today. So Benjamin, the floor is yours.
Okay, thanks, École. So thanks very much to the organizers of SAC for having me virtually. And therefore, thanks to all of you for the honor of being in your living room or in your office, depending on where you're spending the pandemic. SAC is a really nice conference. At least I've only been once, but it was a really nice time. It's a nice community, and so it's really, I would have loved to have been actually present, but it's a funny year, obviously. So what I'm going to talk about is a problem in number theoretic cryptography, because that's mostly what I work on. And it's the problem of constructing a group that you don't know anything about, except that it's going to be efficient and that it's going to be secure, which is a surprisingly tricky problem. This is something that I've been thinking about over the last year or so with Stephen Galbraith and Samuel Dobson, both from Auckland. It's something where, I mean, we've published some notes on this, but it's something where we're still very much puzzling about this. It's something where it's complicated to really say what the right notion of security is in this setting. And that's what I want to share with you is not so much like a finished result, like a great sort of number theoretic gadget that's going to, save the day and solve all of your problems. What I want to share with you is more of a thought process, and then the sort of the puzzle that we're facing with this thing at the end. So these are very much results in work in progress, and the three of us would be very interested in hearing anyone and everyone's opinion on these results. So just to very briefly set up some context for this. So a group of unknown order is used in lots of different cryptosystems. Okay. And these are, when I'm talking about groups of unknown order, I mean, you could say that when you're doing, say, RSA signatures, there's a group of unknown order, which is, posed by the RSA modulus n, for example. But here I'm talking about groups that are where the order is unknown to all of the users of the system. Okay, so it's a global system parameter, this group, and its order is not known. And if you don't know examples of protocols where you use this kind of thing, this appears in accumulators and verifiable delay functions and other sorts of cryptosystems that are that have always been interesting to the theory community, which are becoming more and more interest to cryptographers in practice. And the basic notion here is that if anyone can compute the order of your group, then they can break the entire system for every user. So it's not just, well, if they factor this RSA modulus, then they know the group order for one user. There's one global group, the world that everyone's sort of playing in. And if you can compute the order of that group, then you break the world. Okay. So for an example of something without really formalizing the whole cryptosystem and going into details, you might have a delay function, which is based on something like repeated squaring in a group. So here, most of the groups I'm going to be writing in additive notation. This curly G is always going to be the group. And so when I write a number in brackets here, times P, for example, where P is a group element, the 2 to the T here, the brackets are saying this is multiplication by 2 to the T. So scalar multiplication like it would be on an elliptic curve. So here you can do this obviously by computing 2 times p, then doubling the result, then doubling the result, and so on, and repeating this this operation t times. And since we don't necessarily we tend to treat like doubling as being this atomic operation that we don't really know how to do much faster, and there's up to a certain point we don't really know how to do multiplication by 2 to the t faster than just doing t multiplications by 2. This is the kind of thing that you can use to assure that someone is occupied for a certain period of time, little t here. But if you know the order of the group, then you can reduce this scalar mod the order of the group, because I mean, once you've multiplied by the order of the group, then you get to 0 when you wrap around and start again. So rather than having some enormous 2 to the t, I mean, here we're taking a rather large value of t here, we can just reduce 2 to the t mod the group order and maybe come up with something that's faster to multiply by, because we'll be then we will be multiplying by a number of length log 2 the order of g. Okay, so this will be a shorter scalar, something easier to do. So this is just an example of a task that on the surface might look hard when you don't know the order of the group, but as soon as you do know the order of the group, it becomes a lot easier. And so that's why we want to avoid, this would be one instance where we want to construct a group where computing the order is hard. In some applications, there are even stronger requirements, like the adaptive root assumption and the low order assumption. And the idea here is that, well, not only should it be infeasible to compute the order of g, but it should also be infeasible to compute, to extract roots here. So random mth roots for any m. You shouldn't be able to compute the preimage under multiplication by 2 or by 3 or something like that, or by 7, or by any particular small m. And you shouldn't be able to construct any elements of order m, elements whose order that you know, particularly for small values of m, but in general, just you shouldn't be able to construct any element whose order you know. When I say here, you shouldn't be able to compute elements of known order, if that order isn't reasonably big, then it's probably most of the order of the group anyway. So here we're thinking about things like small values of m, because if you have some element p of your group and you know its order, and that's comparable with some sort of bound on the size of the group that you would deduce from things like the length of the representation.
Ben, you're muted.
Yeah, that was not me that muted me. Okay, so I'm unmuted again. Thank you. Okay, so if you can construct an element of a large order, and that order is comparable with the bound that you have on the order of the group, then you've probably already found most of the order of the group, and that's going to make it easier to compute the rest. So here, when we say known order, we're really focused on small values of m. That gives you a divisor of the order of the group, but it doesn't give you the whole thing, or enough to be really, really useful here. So here you could think of something like m equals 2. Can you find a square root of an element in the group? Can you find an element of order 2? And our reflex, like at the start of the talk, when I said, well, examples of other protocols that use various groups of unknown order, things like RSA. So generally, our reflex in cryptography, when someone says, right, I need a group of unknown order, you put forward an RSA group. Because, I mean, first of all, they're easy to work with and conceptually easy to deal with, but also because you know that computing the order of the group really comes down precisely to factoring the RSA modulus n. So let n be capital N be p times q, where p and q are secret large primes. Then the multiplicative group of residues modulo n. So this is just integers prime to n less than n under multiplication. The number of these is the Euler phi of n, which is p minus 1 times q minus 1. Okay. Now, if someone gives you an n like this, I mean, they have to give you the modulus n so that you can compute with the group. Then if you factor this, you've got P and Q, so you know the order of the group, and vice versa. If you know the order of the group, you can derive P and Q from this. So what's nice about this is you've got like a nice provable reduction to the factoring problem for your problem of computing the group order. And this is the worst case of conventional factoring algorithms. That's why we use it in RSA, and that's this includes ECM, but also notably the number field sieve. When I was talking about not being able to find square roots in a group, for example, here's an example where this is a concern. So it's easy for you to write down -1 mod n. I mean, that's just n minus 1, and you know this has order 2 in the group. Right? So even if you don't know P or Q, you still know one element of order 2, which you can just write down straight away. So if you want to prohibit anyone from having elements of order 2, then you might want to just use the squares mod n. Otherwise, you'd say, well, can there exist like an element of order 3 or something, for example? That would imply that 3 is dividing P minus 1 or Q minus 1, but let's say P minus 1, for example. So if you want to avoid, basically, if you want to block off this element of small order problem, then it really suffices to take P and Q such that P minus 1 is 2 times a big prime and Q minus 1 is 2 times a big prime. And then the only small order for which there are elements of that order is 2. And you can get rid of the obvious element there, or you can get rid of the order 2 problem basically by only using the squares. So using the subgroup of index 2 in this group. Okay, so this is the obvious answer, and it kind of solves the problem when you want to set up a group of unknown order. But first of all, you want to say, well, how big do we have to take n? Or how should you choose n? And so that comes down to the problem of factoring. So when someone has a general integer n, you go, well, how do you factor this? The first thing you do is you do some trial division. I mean, you'd say, well, we'll construct an RSA number n, but why can't we just take a random n and use it as an unknown order group? The problem is if you're going to take an n that's not an RSA modulus, then it will be a little bit easier to find the group. And this is the group order. And this might sound completely obvious, but it's a comparison that'll be useful later on. So you want to factor general integer n. The first thing you do is you do some trial division, okay? Because I mean, if it's a genuine random integer, half of all integers are even, 1/3 of them are multiples of 3, and so on. So you'd be stupid to start up a high-powered algorithm when you haven't already checked for divisibility by the first 1,000 primes or something. That costs you almost nothing to do. Then once you've done that, you do a lot of ECM. This is Leinster's elliptic-curve method. And what's interesting about ECM is that its expected runtime depends only lightly polynomially on the size of n itself. The dominant part of the runtime depends on the size of the smallest prime that divides n. So your sub-exponential with respect to that p dividing n, the smallest prime. This is when you're running ECM, you're trying lots of different elliptic curves and then gradually increasing your smoothness bounds and so on. If you want to really use ECM as your definitive factoring method and you've got nothing else, you will find P after LP 1/2 root 2 Z mod n Z operations. Okay, this means that what you're looking at is the complexity is kind of exponential in the square root of the log of P, or something like this. Okay. So you try this for a while, because if you've got a P dividing n that's too big to catch with trial division, but too big, I guess, also to catch with ECM, you're going to have to try something bigger. Okay. So then you're going to move to the number field sieve, and the complexity of the number field sieve is depending really only on the size of the number n that you want to factor. It's L1/3 in this. So what you want to do is design your number to push you out of ECM range by far and really sit yourself firmly in the worst case, which is where only the number field sieve is going to solve your problem. That means you need to make sure that there's no moderate sized p dividing your n. So you just take n to be the worst case, where all of its prime factors are the same size and none of them are small. So there's only two, p and q, both about the square root of n. And so looking at the asymptotic complexity, but also doing a lot of actual experiments in factoring and looking at the time it takes you to factor numbers of a given size, you can move from just having these asymptotic complexity statements into looking at the actual curve of predicted runtimes for factoring in practice, and you can try to derive some concrete security estimates from this. And we think that at the moment, I mean, the way we all behave is we think that a 3000-bit n, or a 3072-bit n, should provide about 128 bits of difficulty in computing the order of the group, okay, in factoring n, and therefore in computing the order of our group in the end. Okay, so 3000 odd bits should do for something like this. So I was saying you know how to construct a group of unknown order. You're going to take an RSA group. When you want computing the group order to cost 2 to the 128 operations, whatever an operation means, then you're going to choose a 3000-bit n. And you know that you want, like, regardless of what you're going to have to do later on in the crypto system, and what the adversary is going to attack in the end, you know, you really need this setup to be providing 128 bits of security with respect to this problem of computing the group order. Because if some adversary can spend that effort and break the group order, then they certainly get everything else as well. Okay, so there's no point going at less than that when the rest of the system is targeting 128 bits of security as well. So the problem is solved, except in the case that I really want to talk about, which is trustless setup. Okay, so in the trustless setup setting, the idea is that no one should be able to compute the group order, not even whoever generated the group. Okay, and an RSA group is no good for this, because if someone's choosing an RSA modulus, okay, they know the factorization of n. If I choose like a strong modulus, a worst case factoring modulus, something where I can really tell you, well, it's going to cost you 2 to the 128 to factor this, I have to choose a p and a q of the right size. I can't not know them. I can promise you that I forgot them later, but that's requiring a measure of trust on your part. So on the other hand, you'd say, well, okay, let's just take a random n instead. You know, random numbers have some big factors in them. So, you know, like how bad could it be? Well, just not good enough, because random numbers can often be factored, and we use ECM for this. ECM, remember, the difficulty is depending on the smallest prime factor of the number. I mean, once you've chosen small numbers that are not divisible by you know, the 1,000 smallest primes or whatever, then what you choose is going to be made up of medium-sized primes and maybe 1 or 2 large-sized ones. But you'll find the medium ones, and you'll gradually break your problem down using ECM on this, and then by applying maybe you know, some other factoring algorithm to the large piece that's left, but it's a smaller instance of the problem, and so the work factor has come down. You don't have the right security. So you can't just choose a random n, because it won't be strong enough, and you can't just choose an RS, like you can't choose a worst case n, because that means you have to know the group order in advance. So we're going to have to do something else, and there are 2 candidates for this. There's ideal class groups and random number fields, especially imaginary quadratic fields. And then the other candidate that I want to talk about is Jacobians of random hyperelliptic curves. The first candidate here, the ideal class groups are really a classic thing for this. They're the thing that you use when you don't use an RSA group traditionally. So our suggestion of using Hyperelliptic curves instead is kind of a new thing in this talk. There are really strong mathematical similarities between these two groups, but there are really massive differences in how we actually compute their orders. Okay. When I say there are mathematical similarities between these two, I mean, we'll see as we go along a bit, but this is a really classic correspondence in number theory, where on the one hand, you have rings of integers in number fields, and on the other hand, you have rings of integers in function fields, global function fields. And in the number field side, here you get ideal class groups. And on the function field side, here you get Jacobians of algebraic curves, okay, or the theory of algebraic curves. So these things have like a dictionary going from one side to the other, like ideals on the one hand are corresponding to points in the other world, points on curves. You know, there are zeta functions for both of these objects. A lot of the algorithms that work with one kind of work with the other. In algorithmic number theory, working with one has always influenced and fed back into working with the other. So in the abstract, there are really strong similarities between these two, but then there are some really big differences between these two as well. And those differences are really at their strongest, I think, in an algorithmic sense. Although one big mathematical difference between these two, for example, is that the Riemann hypothesis is like a massive problem in number fields, but its analog in function fields, so in curves, is a theorem and has been for a long time. Okay, I mean, it's something you would study in a graduate seminar. So some problems, even though there's really this dictionary and this kind of meta isomorphism between these two worlds, you know, even though we have that, there are still some problems that are hard on one side and easy on the other. And so we're going to have differences between them algorithmically and then cryptographically as well. But within that correspondence and within that dictionary, imaginary quadratic fields, and well, quadratic fields in general, they're really the things that correspond to hyperelliptic curves. So these two, the ideal class groups of imaginary quadratic fields and the Jacobians of hyperelliptic curves, these really are just cousins of each other that we're going to be comparing. And so what we want from these, whatever we choose, we want to be able to efficiently generate a group G such that computing in the group G is easy. Representing the elements of G is easy. Like, you can have a compact representation for these, because in the end, elements of your group are going to end up being your public keys, for example. So you want to come up with the shortest representation for group elements that you can. And also you want computing the group order to be cryptographically hard. Okay, for some applications, you also want finding elements of known order to be hard. We also want to be able to compare, yeah, that's, well, now we've summarized our requirements. What we're going to do in the next little while is compare ideal class groups and hyperelliptic Jacobians as candidates for this. So first of all, class groups, because this is the classic thing. If you haven't seen a class group before, you might have seen a quadratic ring before in some other context. But in general, just let delta be some negative square-free number. Okay, so just a negative product of primes without multiplicity. And we're going to consider the ring of integers in the quadratic field Q root delta. Okay, so root delta is an imaginary number, and that's why this is an imaginary quadratic field. Okay, so the ring of integers, it's either Z root delta, or there's like a possible denominator of 2 if delta was 114. Okay, but in your mind, you can think of this as being something like Z root delta. The ideals in this ring are subsets that are closed under addition, and they're closed under multiplication by elements of this ring of integers here. Okay, so you can make an ideal by taking all the multiples of 2, for example. It's an ideal. Some ideals like that one can be generated by a single element. It's generated by the element 2, but that's not necessarily all of the ideals in the ring. But every ideal can be generated by at most 2 elements. So we can always find a 2-element representation for the ideal when we want to compute with these things. And so the class group then, I mean, if you take two ideals and you multiply them together, you get another ideal. Okay, and the class group is what you get when you take all of the non-zero ideals under multiplication, and then you work modulo the principal ideals. So anything that's principal, something generated by a single element, you are going to count this as being the identity. So this is as if when you're doing your ideal multiplication and gradually building up a bigger and fatter looking ideal, if you eventually get something that's principal, you can reduce that away, okay, and throw it away and get back to the trivial element. It's not at all obvious that this is actually a group if you're just looking at this definition here, because you think, well, multiplying, that's fine, you do that in a group, but what about things like an inverse? And actually, if you take an ideal, there's always a conjugate ideal, which is when you multiply it, you get the norm of the ideal, which is principal. So we want to, like, you don't get a group if you ignore them, like if you include principal ideals as being non-trivial. But given that every element in the group basically can be powered up or multiplied into something that's principal, if we work modulo the principal ideals, then we get a group. This is probably like the worst description of the class group you've ever heard. Even if this is the first description of the class group you've ever heard, it's probably the worst one. So let's look at an example. We'll take delta to be -17, and then the ring of integers is just z root -17, which is something we can work with. So the ideal generated by 5 is a prime in this thing. Okay. The ideal generated by 2 splits though. So 2 is no longer prime in this ring. It breaks into two prime ideals. And here we're seeing what I mentioned before about this two-element generator situation. So the two primes each have two elements generating. One element is 2, and the other is 1 plus root -17 or 1 minus root -17. Okay, so take one of those ideals. The first one, this is a prime, and it's not principal. Okay. There is no element of the ring that you can multiply by something to get 2 and multiply by something else to get 1 plus root -17. Okay, so you really need the two generators. But when you square this ideal, so you square the generators and you cross multiply them, and then you look at what multiplies into all of these. I mean, when you take 1 plus root -17 and you square it, on the one, you're going to get -16 plus 2 times root -17. Plus there's like a 4 over here, and there's a this and this, and you play all these elements off against each other, and you discover that actually everything in the square of this ideal is a multiple of 2, which is principal. So in the class group, this ideal has order 2, because when you square it, you get something trivial, the ideal 2. The ideal 3 also splits in a similar way. When you square this ideal though, you get something, you can see it's a bit fatter, in the sense that its generators are gradually getting a little bit bigger. 9 and 2, here we're only squaring, so they're not going to get very big. You square again, well, the result of squaring was not principal, but you square a second time for the 4th power. Again, the number of bits in your representative is growing a bit, but in this case, it's actually principal. Everything in the 4th power of this ideal is a multiple of 8 plus 2 root -17. Okay, so the class group has order 4, and it's generated by this ideal 3, 1 plus root -17. I mean, nothing I've given you here is a proof that it has order 4. That's just an assertion. But then, having accepted that, here we have a generator for it. So how big is the class group? For big discriminants delta, so as as minus delta sort of heads off towards infinity, then you expect your class group to have order half of the square root of delta, or of the absolute value of delta. So yeah, it's basically growing with root delta. This thing. When I say this is approximately, this is if you look up like the Brouwer-Siegel theorem and this kind of thing, you get more precise estimates here. But root delta will do for us. So that means that if you want a big class group, you just choose yourself a large negative discriminant. Okay. if you, like if you want to be sure that this really is the way that it is, you could do something like take delta to be minus a prime, okay, for a really big prime. And then if you manage to choose a really big prime so that the class number is not on the order of, like if it's substantially smaller than this, then you've found a counterexample to the Riemann hypothesis. So, class numbers are big like this. And I mean, we just saw that we took delta to be minus 17, we got class number 4. I mean, this is a very sort of small thing, but yeah, you can see it's, well, that's kind of a fake witness to the idea that it's roughly square root. Anyway, okay, so when you want to compute in the class group, this goes back to Gauss. Working with class groups is old news. It's a really old thing. We use this composition and reduction of binary quadratic forms. Here I've got a little bit about the representations and the elements of these things. The main point here, without spending too much time on this, is that when you want to work with an element of the class group, it's going to take you roughly log delta bits here. Okay. Basically, because we can convert this ideal representation into a binary quadratic form, which is a quadratic polynomial. So its coefficients are A, B, and C, such that maybe I can shrink this thing away, such that the discriminant is delta. But you can choose the polynomial representing this in such a way that that B and A are, in square root delta, and you don't need C because it's determined by the other two. So we can therefore encode this just using this this small version of A and B, which is going to take about log delta bits. We've found in the course of this investigation, we've found that you can actually compress these things to 3/4 of log delta bits for transmission. So that's kind of we can't see a way of getting smaller than this without factoring the number A, and we're assuming that factoring is generally difficult here. So yeah, we can't really see a way to get smaller than 3/4 log delta bits for your public keys in this setting. Okay, so quadratic class groups have a long history in cryptography. This goes back to Buchmann and Williams in 1988. So this is, like just after the introduction of elliptic curves in cryptography. When Miller and Koblitz are proposing elliptic curves for doing a Diffie-Hellman, well, like a couple of years later, Buchmann and Williams are going, well, here's another group where you can do Diffie-Hellman. But at first, they didn't have an efficient group order calculation thing, so it was hard to say whether the group you were using was secure or not. Hafner and École then came up with this L1/2 algorithm, and L1/2 is sort of comparable with old style factoring, like 1980s factoring, like the quadratic sieve, to compute the order of the class group. Okay, so then if you did a big computation, you could come up with a known class group order, but you could argue that this was secure with respect to things like the Polytechnique reduction and this kind of thing, to talk about the security of Diffie-Hellman in class groups. Okay, so this then feeds into algorithms to compute discrete logs in class groups, which, I mean, there's been plenty of work on this over the years. Although there hasn't been much sort of concrete work on these crypto systems, like in terms of actually putting them into practice, so you can, things where it comes down to questions like key compression and speed ups and optimization. There hasn't been a lot of that done over time, mostly because the keys in this thing just ended up being so much bigger than they are for elliptic curve crypto systems. Okay, so elliptic curves really got the jump there because they're compact, and since they arrived just before class groups, it's not as if people had like a 5-year start on using class groups and then went, oh, hang on, should we use these elliptic curves? They're a bit weird. Everyone said, should we use elliptic curves? They're a bit weird. And then they went, yeah, well, these class groups are possibly weird, but also much bigger. Okay, But there's been security estimates based on these algorithms, at least. So even if we don't have like running times and so on, performance estimates for these cryptosystems, we do know roughly what sort of parameters you would want. And so more recently, given we know that computing the group order is sub-exponentially hard, we go, well, like if we just take the group order big enough, we won't be doing Diffie-Hellman with this anymore, but it could be a trustless unknown order group. If you took delta to be minus a big prime, like minus a 1665-bit prime, for example, then that would be giving you an 800-bit group. And the idea is that, based on experiments where these algorithms have been run, or where improvements of these algorithms by like Jacobson and Vollmer and then other people, this should provide you with about 128 bits of security. You have to watch out in these sorts of groups. I mean, just choosing a random delta or a random looking delta is fine for giving you a group whose order you don't know, but you can have some issues with the low order element assumption. So here are some examples of this, and so there's this recent work of Belabas, Klemniuk, Sanso, and Veselovsky. When I say 2020 here, the preprint's been up for 3 days, so this is really new stuff. But this is a really nice paper, and they give these really nice explicit constructions of kinds of delta where you can explicitly violate the low order assumption. So for example, if you take a delta in this particular form here, 4 times a power minus a square, well, the negative of that, where the power and the square are both odd, then you can write down immediately an element of the group. You can write down an ideal that has order t in there, so the order of the power. That's that's really nice. So the thing with this kind of construction here is then, well, obviously most random primes are not of this form, but it would be possible to like maliciously choose a prime in that form, and then you'd go, well, who would know? Because there's a lot of room for randomness in the choice of U and B and so on here. Okay. Anyway, that's class groups. What we're sort of thinking here, what people have been proposing, basically for the last 20 years or so, is something like 1,500 bits worth of delta in order to get 128 bits worth of group order hardness. Hyperelliptic Jacobians. You've probably all seen elliptic curves. Some of you saw them on Monday. So an elliptic curve is an equation like y squared equals x cubed plus ax plus b, or that's your defining equation. The points satisfying this equation together with the point at infinity form a group. The order of the group is approximated by Hass's theorem. It's basically q plus 1 up to some correction term, which is bounded by 2 root q. Okay, so you've got roughly q points in this thing. I mean, the top half of the bits of the group order is the same as the top half of the bits of q. Right. And when you want to work with elements of this group, it looks like you've got an x and a y, but you can get rid of y up to like a sign bit, because once you've got x, y is one of the 2 square roots of the defining equation. Okay, so it's easy to recover y if you just keep this bit. So that means an element of this group is going to take log q bits to store or to transmit. The group law, without showing you like the usual chord and tangent diagrams, the group law is algebraic. Right, so we've got polynomial formulae that will compute the group law on an elliptic curve. And then if you take those, I mean, that tells you that, we're going to be able to efficiently compute the group law and use the group and do all these sorts of things. But for us today, what's interesting is that if you take that group law and you basically iterate it, and you can do this recursively using these occurrence relations, you can compute division polynomials out of this. You can basically derive an expression that has to be satisfied by anything such that m iterations of the group law will give you 0 in the group. So for each integer m, you can compute this thing called a division polynomial. This depends on the curve e. Its coefficients will appear in the coefficients of the polynomial. such that psi m of x of a point is 0 precisely when m times that point is 0. And these polynomials, I mean, they're kind of straightforward to compute, but the degree is like if m is odd and co-prime to q, which is the general case, the degree is m squared minus 1 over 2. Okay, so the degree is growing quadratically in m, and that means that m is going to end up being reasonably small for you to be able to compute these things. I mean, we can compute division polynomials going into the hundreds and thousands and whatever if you like, but compared with the group order, which is going to be something like 2 to the 256, you know, we're not going to be able to compute division polynomials for anything particularly large. So the point of this is if you want to find a point of given order, like if you want to find a point of order 2 or of order 7 or whatever, you can compute division polynomials and look for their roots. Right? And that's perfectly efficient if m is small. And when I say small, like polynomial in log Q. So elliptic-curve cryptography was proposed in 1985 by Miller and Koblitz. And up to that point, well, up until just before that point, we were computing orders of elliptic curves for all sorts of other things in mathematics. And we'd be using generic algorithms to do this, things like just brute force. You know, so when Birch and Swinert and Dyer were coming up with the BSD conjecture, they were computing group orders using brute force. These were very small group orders, of course. And then since then, like, you know, that was like 60s or something, and coming through the 70s, there's Pollard Row and baby step, giant step from Shanks, and these are both square root algorithms. So they work in any group, actually. So here I'm putting a curly G. The time for these is square root of the group order, and the space is O of 1 for Pollard Row, and the space is also square root for baby step, giant step. But in the particular case of elliptic curves, since these are not abstract groups, if we get a bit more specific, you can apply baby step, giant step to the correction term in the group order in House's theorem, to the trace instead, and then you're shrinking down the search space, and you can do this in the fourth root of Q instead of the square root of Q. Either way, this is still exponential. And so it was really revolutionary in 1985, or a couple of years before, when Schroff developed his polynomial time point counting algorithm for elliptic curves. The way this works, without going into a lot of detail here, I mean, there is a lot of detail on the slide, but you can always come back and look at this, you know, sometime when you want to hurt your eyes. The point of this is that you compute the elliptic curve. Essentially, you compute its order modulo a bunch of small primes, and then you're going to glue the results together using the Chinese remainder theorem. And for each small prime, what you end up doing is you're computing the action of Frobenius on a generic L torsion point, and you're constructing that L torsion point by using the division polynomials. So the really important thing in all of this is buried in all this notation: compute psi L of x, right? You've got to compute the division polynomial. And then throughout the rest of the algorithm, all of the operations that you do are basically polynomials that are being reduced mod psi L all the time. So the bigger the division polynomial, the worse this particular L is going to be. And the complexity ends up depending quite heavily on the degree of your division polynomials, which we know is L squared minus 1 over 2. So when you put the complexity of this whole thing together, you get like a log to the 5th FQ operations if you're using fast integer and polynomial arithmetic. In the early days of elliptic curve cryptography, I mean, when Schroff published this, he was just using like schoolbook arithmetic. So this is log Q to the 8th. And so this algorithm, if you look in like the early ECC papers, people didn't think this algorithm was practical. So they were constructing elliptic curves using what's essentially the CM method to come up with, or a forerunner of the CM method to come up with secure group orders. But once people started looking at Schroff's algorithm, Elkies and Atkin improved this, especially Elkies, by replacing the division polynomial with an isogeny kernel polynomial of lower degree, and this brings down the complexity by a factor of log Q. So this becomes quite fast. I mean, like a polynomial degree 5 is feasible. Degree 4, well, you know, that's all right. You know, we don't mind running this when it's for system setup. And you can, I mean, see implementations are all over the place. I mean, in like Paris GP, for example, or Magma or whatever. So computing large group orders is routine, and that means elliptic curves are a bad source of unknown ordered groups. So why would I tell you about them at such length? Because in this sort of like mid to late 1980s gold rush of everyone showing up with their own favorite group to use in cryptography, elliptic curve groups, ideal class groups, and then Koblitz comes back with hyperelliptic curve cryptography. And here you're, instead of y squared equals a cubic, you've got y squared equals something of degree 2g plus 1. G is the genus of the curve. And rather than the points on the curve forming a group, multi-sets of up to g points on the curve form a group, which we call the Jacobian. And this is really, really closely related to the class group of the function field, you know, up to some, you know, technical quibbles. So here we're really thinking of class groups. Class groups are quadratic things because you can see you're basically adding a square root of this polynomial f to your function field. So you're adding a square root. It's a quadratic thing that you're making here, a quadratic field, quadratic function field. Right, here you can collect your g points on the curve that are forming an element of the group. You can encode this using a pair of polynomials that encode and interpolate their coordinates, and you can compress this down to just g elements of fq plus some sign bits. So we're looking at g log q bits for transmission. And the number of elements in their group, this works out pretty well. It's basically q to the g. More precisely, so here's like the Weil bounds, which is giving you the analog of Hass's theorem. It's really q to the g plus some lower order terms in root q here. And so computing exactly what that is, this group order, this is really a classic problem in algorithmic number theory. And your input is like a curve of genus g over fq. The holy grail, if you write q as fp to the n, is an algorithm that's polynomial in the input, which is the curve equation, which is basically a vector of elements of fq. Each element of fq is a vector of length n of elements of fp. So your parameters here, it's g log p and n. And no one has a point counting algorithm that's polynomial in all three of these at once. There are two things that are worth noting. First of all, Pila wrote down like a Skov-like algorithm that works in arbitrary dimension abelian varieties, which includes these Jacobians. And it's polynomial when g is fixed, but this algorithm's never been implemented, basically because this polynomial exponent hides this awful dependence on g, which is constant. Okay, so is a polynomial in log p and n, is polynomial in fq, in log q, but really bad with respect to the genus. And then Kedlaya later on, and this was a real breakthrough, solves the problem for much higher genus. Like he's polynomial in the genus, he's polynomial in the field size up to a point. It's just that he's exponential in p. So if you were doing this in characteristic 2 or 3 or like up to 1,000 now or something like that, this can work in really high genus, which is cool. But if you're working over a cryptographic size prime field, you'd be stuck. So we focus on this case, and the theory says that point counting is polynomial time. So we think it's easy, but practice tells us that polynomial point counting is polynomial time, but it's actually ridiculously hard, which is sort of a bit of a cognitive dissonance. And all of the recent progress in the problem is following in this L-adic Skov-Pila sort of direction. Genus 2, for example, is p to the 8th. For the sort of general algorithm. If you use special families of curves, you can get down to p to the 5th. No, this should be log p to the 8th and log p to the 5th. Okay, clearly not p to the 8th and p to the 5th. So you can improve the complexity a little bit if you constrain your class of curves a lot. But for a randomly chosen genus 2 curve, this is going to be slow. And the record computations, we're looking at 128-bit fields. Which is like contemporary discrete log sized things because the group has p squared elements roughly. Okay, so why is this so hard in genus greater than 1? So genus 3 has only recently been implemented for the first time, and even then only partially. We'll get to that in a bit. Why is it so hard? Basically because your division polynomials are replaced with ideals. These ideals are ideals in many variables. the number of variables is growing with g, and the degree of the ideals is like the division ideal for m is like an m to the 2g. Okay, remember this is like O of m for elliptic curves. So you can see where, like m squared for elliptic curves. So you can see where the g is sneaking in here. This is where the g is coming into the exponent of the overall complexity. So when I said like the exponent had this terrible dependency in Peeler, it's even worse than this. Okay, but you can see there's at least one g that's going to pop in there. And so there's recent results. So this is a purely theoretical result of Abelard and Gaudry and Spanlauer, where they show that, well, there should just be one g popping into the exponent of the complexity of point counting here. You can still work with division ideals for very small L, like I2 is just telling you about the quadratic factors of the hyperelliptic polynomial, or the factors of the hyperelliptic polynomial. Here, quadratic in genus 2, but more generally other factors of the hyperelliptic polynomial. And I3 you might be able to try to manage, but this is going to be really, really fat, etc. Okay, so we would argue that finding elements of order L is feasible when L is very small, even if point counting is not. And if you iterate these sorts of tricks, you think, okay, well, we might be able to find elements of order 2 to the n, for example, just by repeatedly doing the element of order 2 trick. So in practice, when you're doing point counting in genus 2 already, you do this Scoff approach for a bunch of small L's, and then you've partially solved the problem because you've found the order mod the product of those primes. But that's not enough to determine the full group order because your product of primes isn't big enough. But you've hit this wall where you can't work with the division ideals anymore. It's just too heavy. And at that point, you switch over to an exponential algorithm and you finish with that, which is this really crazy situation where you abandon a polynomial time algorithm to move to a clearly exponential one to save yourself time and effort. Genus 3, it goes in the same direction, except here L is even smaller. So I think like in 2018, maybe there was one L involved in a point counting computation that was 11 or something, and that was epic. You know, that was worth writing a paper about. Okay, so you also have to rely on exponential methods in genus 3, and there's been no point counting done in genus 4 and above. Okay, in genus 3, it's clear that this is already a complete pain. So is this really practical, point counting? And our answer, Stephen and Samuel and I would be, well, yeah, genus 1, yeah, I do it on my laptop. Genus 2, you want a cluster. Genus 3, it's not really practical at all. Genus 4, no. And genus 5, you know, no one even wants to think about implementing this stuff. And we interpret that to mean that the best point counting algorithms are basically still exponential methods like square root algorithms like Pollard Row. Apart from a little bit of modular information that you might be able to get from doing like L equals 2 and 3 or 11 or something like that, but you can't go very far with that. So we would estimate that for genus 3, if you choose a random 100-bit prime, or choose any 100-bit prime you want, and then choose the random genus 3 hyperelliptic Jacobian, you should be getting about 128 bits worth of point counting difficulty, and therefore 128-bit security, seen in this way as a trustless unknown order group. The thing that I want to mention very quickly is Sutherland's algorithm, which is something that's not very well known in our community. And this goes back to about 2007. We've been studying class groups and their orders for a long time, going back to Gauss. And before we had Hafner-École, like Shank's baby step, giant step was designed for computing class group orders, for example. So we've been using generic algorithms to compute class group orders and developing class group order algorithms that have ended up becoming generic group algorithms. So baby step, giant step is an example here, but we're going to just skip over this very quickly. These algorithms like this run in square root time. And up until 2007, people generally believed that since the same algorithms applied to discrete logs, I mean, really the same algorithms, and Shoup had proven that in a generic group that you know nothing about, it really is a square root problem. People really thought that computing the group order was also a square root problem. And so Drew Sutherland came along in 2007 and kind of blew that completely open by proving that you can always do better than square root n for computing the group order. And his algorithm depends not just on the size of n, like the worst case when n is prime is like you're saving a square root log n factor, which is basically nothing. It still counts asymptotically. But what really counts is the factorization of n. That has a big influence on the runtime of this algorithm. And for what's interesting here is the median complexity, which is for nearly half of the inputs, for nearly half of the possible group orders, the runtime is only n 1/3. And for a smaller proportion, it's even less. You do this using the primorial step algorithm. So it's a very simple but subtle modification of baby step, giant step, at least in the first instance. I won't go into depth on this because I would also like to really suggest that everyone actually read Sutherland's PhD thesis. It really is a modern classic. It's the kind of thesis that you read and like every page you're like, oh, this is just great. And you learn something that's really relevant and useful in the end. What's important is that the running time of this algorithm to compute the order, the probability that it will succeed in a certain time depends on the semi-smoothness of the group order that you're looking for. So if you, well, we have this expression here, which says that the probability that you will run in less than uth root time comes from it's bounded below by this semi-smooth probability function. This is something where we can compute this numerically. And so here is the same probability, but here with a table of values for g of 1 over u and 2 over u. And so what this is telling you is that, well, when u is 2, that's square root, and you can always solve the problem, okay? But as you start to say, well, let's go a little bit faster, you can see, well, there's still like 1 over 2.5, 73% of the time this is still going to work. Like 1/3, this is still going to work like you know, a substantial amount of the time. And this comes down to, well, okay, so by the time you say, okay, I want this to run in like 6th root time, this is going to work like 1 in 1,000 groups or something like this. Okay, but we can push this analysis a lot further, putting in higher values of u into this. And we end up with this situation here. And this is what I kind of really want to show you. When you're randomly selecting a class group or a hyperelliptic Jacobian, whichever one you want, there's a non-negligible chance that Sutherland's algorithm is going to be able to compute the order. And you have to take that into account when you're selecting your parameters. Okay, so here, the rows here correspond to the time that you're willing to spend. You know, like if you've got 128 bits worth of attack, you're on the bottom row. But if you're just willing to spend 55 bits worth of effort, you're on the top row. And then if you're willing to accept your group being completely breakable for everyone, so having a weak group order with respect to Sutherland's algorithm with probability 1 in 2 to the 40, then that means you can get away with a 660-bit group order here. So in particular, that means that, like I was saying, well, just take like a 100-bit prime for your hyperelliptic curve. That's giving you a 300-bit group order, but that's not going to defeat this kind of an attack here if you're just choosing a random one. I mean, Sutherland's algorithm, there's a fair chance that that we're just going to blow up the group with it. It's I mean, it's a very tricky situation because you're being given one group. Okay, it's not as if we're saying, okay, like what's the average case complexity? You know, like there is one group to be attacked, but it's a random group. If it's a class group or it's a Jacobian, then its order is more or less uniformly distributed over this interval. You have to attack that one, but there is a chance that it's easy. And so that's basically where we're at. We want to propose random hyperelliptic Jacobians as a competitive option for unknown order groups with trustless setup. Okay, this means we can Well, first of all, we get much shorter keys with this, even taking Sutherland's algorithm into account, because it's attacking both groups equally. So the key size looks good. In terms of efficiency and speed, well, we don't know, because I mean, we don't really have any data on the class group things for this. The security estimates for these, though, are traditionally made with respect to worst case algorithms like number field sieve and Huffman-École and Bookman and Jacobson and Bias and so on. Okay, so we usually use those algorithms to work out what the security should be for these groups. But the point we really want to make is that the complexity of computing the group order also depends on the factorization of the group order using Sutherland's algorithm, which should be better known. And this is something we really have to take into account. But this begs the question of, well, what chance of a weak group are we prepared to accept? Are we really going to say, well, there should only be like a 1 in 2 to the 128 chance that the group is weak and attackable by something with time 2 to the 128? Or is it more like a 1 in 2 to the 80 chance of a weak group is enough, provided it's then going to be expensive to attack? Or there are more dimensions to this problem than it seemed to be in the beginning. And so fitting this into the security model and coming up with an appropriate definition of bit security for unknown group order protocols is more complicated than I think we, and by that we I mean not only Stephen and Samuel and I, but also the wider community. It's more complicated than we thought. Anyway, that's all I have to say here. There'll be a revised, heavily revised version of our notes on this coming out in the not too distant future. And in the meantime, therefore, we'd be really happy and excited to get any sort of thoughts or feedback or opinions from anyone here to apply your expertise to these sorts of problems. So thank you very much. I'll stop this here.
Thank you very, very much, Ben. I don't see any questions in the Zulip channel. Oh, here's Jonathan asking if you're doing a one-time setup by generating this group of unknown order. Can you test if Sutherland's algorithm will work for your selection, similar to a wiki test?
So you could test it in the sense where you just run Sutherland's algorithm and see if it works. Okay, like you just run this thing. I mean, Sutherland's algorithm is something where like you apply it to some group that you've just generated. It will just run and run and run and eventually possibly hit its worst case runtime. Okay, so it could take all the way up to there, and if you stop it a bit early, you'd be like, okay, well, it passed the test up to this point, so it's probably not too weak. But if you can run the algorithm up to that point, then your adversary can always run it at least that far, maybe a bit further. So it's you can, there's no kind of simple test on the number that tells you how Sutherland's algorithm is going to perform on it, apart from looking at its factorization, which in theory you don't know. So yeah, so you can try, but this is in the same way that you would try like a trial division on something and then go, well, okay, I couldn't find any prime factors after this point, so I stopped using my exponential algorithm, and then someone comes along and finds an actual factor not much further beyond, for example. It's maybe not a very clear answer to the question.
I think it gives the essence of the fact that once you stop, you can always try harder. If you know all these cartoons of people digging until they reach diamonds, and then you stop just before the right answer. You reach the diamonds.
There's no sensible notion of where you should stop with this thing.
I think Ian has a question. Ian, if you want to unmute yourself or write it in the channel. Or...
Yeah, thank you. So earlier in the talk, you had this in a slightly different setting, but in the setting of the Jacobians of hyperelliptics, is there a danger that you could maliciously choose a non-random P such that the chooser of the P would have an advantage in learning the group order?
I think in terms of P, not really. Where you would be able to get an advantage would be in maliciously choosing the curve. Okay, so yeah, I mean, you've got a choice of P, but then you've also got a choice of curve equation, varying the coefficients on the polynomial f. And varying that polynomial, you're varying the group order within the same range around P. All of those group orders, I mean, if you chose another prime extremely close to P, a lot of those same group orders would appear for curves on the next prime. So the weak group orders can appear in both cases. But for example, like maliciously choosing the curve, I think would be much more fruitful. If you just for a really simple example, if you take your polynomial to have a factor, then it has a point of order 2 in the Jacobian. Okay, so and you can force more points of order 2 by taking a completely reducible f. And of course, it's obvious to sort of tell if your f is reducible or not. I mean, anyone can see that you tried to pull this trick. But you can do similar things where you play with the form of f, like if I go back to this Veselovsky thing. Yeah, so these families here. So you're taking your delta to be in a particular form. Remember, like the delta, the thing you take the square root of, this is really like the f in the hyperelliptic setting. It's really like that polynomial. So by taking your polynomial in a special form, you can force there to be elements as well. Maybe to really use some of these tricks in that direction, you would have to take the genus to be particularly high, like use a large degree f. But I think there are some symbolic tricks that you could play like this just by taking your f to be in a special form, but still with enough parameters, let's say, that you can get a fair amount of entropy in the thing and have it look moderately random. That's just speculation, but I really think it's more about manipulating f than manipulating the prime p.
Right, thanks.
Are there any other questions on the Zulip channel? Just a second. Yeah, and we have a question from Sam. As far as I know, group of unknown order is impossible in a post-quantum world thanks to Shor's algorithm. Are there subtleties to this, like some way to thwart Shor's algorithm?
I don't have anything quantum to say about this because it's all basically like a pre-quantum thing. I mean, Shor's algorithm is an order-finding algorithm anyway, right? So it's or like a period finding thing. So yeah, as Sam says, yeah, we shouldn't be able to solve this this problem, like proposing unknown order groups in a quantum setting. So everything I've been talking about here is like openly, deliberately pre-quantum, and I have no like post-quantum reflections on this whatsoever. Sorry to be disappointing there.
Well, are there any other questions? Jean-Francois is asking, last slide, you suggest families of curves with fixed genus G equals to 3 and increased field. Does this mean the attack would be polynomial in the input? If the suggested family has an increasing genus, how does this impact the efficiency of the system?
Okay, so hang on. This is a long question, right? So hang on, I can read it as well. Yeah, so the attack, yeah, like when we say use hyperelliptic curves, genus G, like we've taken genus 3 because we think this is already hard enough. You know, if you think, well, like a progress in genus 3 point counting might one day be significant, we'd say, well, just make it genus 4. Okay, it's not going to change the efficiency of the scheme that much in the end. I mean, we can choose a genus 4 thing of comparable group order probably, but with much harder point counting. And the point counting for these things, technically, it's polynomial time. Okay, like really, if you look at, say, Simon Abelard's thesis, there's polynomial time point counting algorithms. There's a lot of analysis of this stuff, but there's a reason why these algorithms have essentially not been implemented, and it's because they're so painful to run, really. Even if you look at like genus 2, if you're looking at like the division polynomial for L equals 19, I mean, this is a polynomial of degree 9. In genus 2, you like the degrees of the polynomials in this ideal, like the messiness of what's going on is more like in the hundreds of thousands. Okay, so it's things rapidly get really bad with this. And so with genus 3, yes, the attack is polynomial. The idea is just that your polynomial is so big and bad, and the algorithm is so awful to run that it's actually, on concrete parameter sizes, this is far worse than an exponential attack. So if we increase the genus of the curves, what that will do is it will make those attacks worse and worse and worse. Like we could say, let's use genus 10 hyperelliptic curves. And I think there's precisely 0 chance of anyone ever doing general point counting on a random genus 10 hyperelliptic curve over a prime field of like a cryptographically interesting size. I think there's no chance of this ever happening, basically, because I think, we'll have burned up the world and its resources, within my own lifetime, let alone the lifetime of a genus 10 curve. But no, I really think this is ridiculously hard. That then you would be able to choose P because, with respect to log P, you're relatively friendly, I guess. You could choose it to have a group order that's, on the one hand, big enough to resist this point counting and big enough to resist things like Sutherland's algorithm for the group order computation afterwards. Efficiency, I think the difference would not be that big. I mean, the group operations would be a little bit heavier, but not in a sort of end of the world sense. But there hasn't been a lot of recent implementation work on high genus curves. So, who knows? If people were really motivated to do genus 10, for example, then maybe we'd have a bunch of highly optimized, vectorized genus 10 hyperelliptic papers suddenly appearing in SAC and chess and so on, and we'd see. But I don't think the difference would be enormous. It's just enough that you think, well, why would we? Genus 3 should be good enough. It's a very long answer to a question, and I hope it addresses some of the concerns.
Well, I think it's about time we let you off the hook. So thank you very much, Ben, for yet another great talk. And we're taking a break until for the next 16 minutes. See you all in the last session in 16 minutes. And thanks again, Ben.
Thanks once again to everyone for being here, and have a really nice day full of talks here.